my clock hit the hour, so I think we're ready to start. Welcome everyone to day 3 of pre-strings, the most exciting part of the whole string event for sure. And today I'm very happy to be again your chair for this first block in the morning, afternoon for me. And we're going to start today with the last lecture of Madalena, lecture number 3, on the very interesting subject of conformal bootstrap. So Madalena, please go ahead.
Thanks. So again, please let me know if there's any issue with the audio, if people can't hear properly. So let me just start by kind of picking up where we left off and saying what we were doing yesterday. So we were studying the 4-point function of 4 identical operators, and we went to Lorentzian signature such that these cross ratios became real and independent variables. And then we had put the operators in this, use conformal symmetry basically to fix the operators in these locations. So we had one at the origin, one at 1, one at infinity, and another operator at position z bar, where z and z bar are now 2 independent real variables. And then what the limit we studied was the limit where this operator approaches the light cone of that one. And then in the end, we end up taking a double light cone limit, and it also approaches this light cone here. And we were studying 2 different ways of basically evaluating the same 4-point function, which were the S channel, which is an expansion between the OP of these 2 guys, and the T channel, which is the OP of these 2 guys. And we saw that crossing symmetry relates low twists in this T channel to large spins in the S channel when we take this light cone limit. So this is the equation we wrote down. And here I did not take z bar to 1 because this infinite sum over spins does not commute with the limit, with the light cone limit of z bar to 1. So here we are inferring stuff about the large spin behavior, where on this side we saw that z bar to 1 is controlled by the lowest twist operators in the theory. So the lowest twist operator we got was the identity, whose coefficient is just fixed as a normalization. And just trying to reproduce the identity on one side from the other side told us that there had to exist double twist operators, which are operators whose dimensions approach this value as the spin goes to infinity. And today I wrote for you, I told you yesterday we could fix the OP coefficients, and now I just wrote the large L behavior of the OP coefficients, so there's something explicit to look at. Okay, and then this was just reproducing the identity. And in the leading z bar to 1 limit and z small, this is how the identity contributes, but the whole identity, if you look back at the crossing equation, you'll see is this. So then matching also bleeding powers of z just from the identity would tell you that all of these operators were here, with n being an integer. Okay, so n is an integer. So all these double twist operators are there, and we can now, you know how their OP coefficients behave. And this is just for n equals 0, I believe. I just wrote the leading one. Okay, then I ended up by very quickly saying that when we have subleading operators here of some twist, we can then get corrections to this behavior. So let me, before moving on to the inversion formula, just quickly go over how this works. So what is the subleading twist that appears here? So we had said that unitarity ensures that there's a twist gap, the identity has twist 0, and the first operator with the lowest twist has either twist above this value if it's a scalar, or above this if it's a spinning operator. So the things that appear with lowest twist are either low dimensional scalars or spinning operators at such a rate is bound. And these are exactly conserved currents. So lowest twist with spin bigger than 0 are conserved currents. So at L equals 1, you would have some current for some global symmetry, some symmetry that commutes with the superconformal algebra. For L equals 2, you have the stress tensor. And that's actually it. Interacting series should not have conserved currents of spin bigger than 1. Otherwise, they are essentially free. So this is work by Madalena and Gioedo that says that with higher spin, which I mean L greater than 2, they're essentially free. So then we have that the next operator that contributes. Let me ignore for now the existence of low-dimensional scalars, but then the next operator that contributes are two spins and the same twist. If there are conserved currents, if there are no conserved currents, it would be just a stress tensor, but there's no infinite sum over spin with the same twist that I have to worry about. So again, there's some discrete twists. So things change slightly if you're studying free series, where now you have an infinite sum over all spins of exactly operators with exactly twist d minus 2. And now we do the same. We have, if we keep looking at this crossing equation, now what we were doing, well, we were saying that the z bar to 1 behavior is matched by the large spin. So by the different z bar behavior, I will get a slightly modified large spin behavior of the OP coefficients. But we were also matching powers of z. And the power of z here is what told us these dimensions. But now the power of z will get modified by this piece of the block. And this piece of the block is actually something I had written in the previous lecture, and I copied down here again. And it basically behaves as a log plus a constant and then subleading terms. So what is this telling us? Remember in the S channel, we had something like this. And I was telling you that operators should have dimension then 2 delta phi plus L to match the T channel power. So in the T channel, we had Z to 2 delta phi. No, sorry, Z to delta phi only. So this is the matching we did last time. And now I find that I have this, and then plus also terms that are Z to the delta phi log Z. So this is telling me that here I will have some anomalous dimension. So I'll have the dimension being 2 delta phi plus some small gamma, where this is an anomalous dimension. Well, I'm calling it an anomalous dimension. It's a deviation from the exact double twist value. And this is approximately this. So then exchanging other operators in the T channel that come with their own blocks that have these log terms are telling me that the dimensions are not exactly double twists, but there are some small corrections. Okay, so again, keeping in the T channel, let's consider the smallest twist operator that has twist OM in T channel. This is then telling me that the double twist operators we discovered have dimensions that are 2 delta phi plus 2n plus some gamma that depends on L. And now you can compute this gamma from this information. And you can then try to set up some perturbative expansion in large spin. So you can do perturbation calculations in 1 over L, where you compute 1 over L corrections from T-channel operators of low twist. And this was done by many people, and it really worked very well. And as I ended the lecture by saying, all I can really say here, and this is even with, so I had here a comment that in all of these derivations, there are various non-rigorous points, and there's a paper that tried to start putting some of these on a more rigorous footing. But ignoring all these little subtleties, what this is still telling me is something about the asymptotic density of operators at very large spin. You know that the asymptotic density has to be such that operators have these anomalous dimensions, and you can compute the corresponding P coefficients, but it's still some asymptotic density of operators. It doesn't tell me anything about individual operators being there. And it's only for large spin, so you would never think it tells you something about operators of spin 4 or 6. And the remarkable thing is that when people started playing these games, the answers they got actually really matched the numerics. So the very first plot I showed in the first lecture, the results of this expansion in 1 over L that you can then try to resum and so on, it actually matched very well even for low spin. So there's something deeper going on here, and what is it? You know, why did this work better than you would naively feel entitled to? And the reason behind this is analyticity in spin. And this was established through a Lorentzian inversion formula. Of who? Okay, so now I finally, I've been progressing through the history of the subject, and now I finally reached the past few years. And let me give a reference for this. We will now see what the Lorentzian inversion formula is and how it relates to light cone, and somehow this intuition that is built from the light cone is still there. So it will be useful. So this was the original paper that obtained this inversion formula, but you can also see an alternative derivation. Perhaps it's physically more transparent here. And here generalizations for spinning operators. So the inversion formula will, as you notice, I'm always restricting to scalar operators because things are simpler and we don't have index structures to deal with. But things have been generalized for spinning operators as well. Okay, so what's the idea behind this analyticity in spin? How do we get it? And what's the inversion formula? So the idea is to invert the OP. So with solid correlation, 4-point functions are fixed in terms of this function of two cross ratios. Remember, I was going back and forth between U and V and Z and Z bar. And then this correlator admits decomposition in conformal blocks, as we discussed. And this is a function that is single valued in Euclidean signature. So when Z star is Z bar. So now I went back to Euclidean signature. I will want to go to Lorentzian in the end, but I will start with the Euclidean OP. Okay, so this is the OP, but now let me write it in a different way. Let me decompose this correlator in a complete basis for single valued functions. So write a complete basis for single valued functions. And these are some, let me call them F delta L. And these are some combination of the conformal blocks with them factors. These are just functions of delta and L that basically involve gamma functions. And it's a combination of the conformal block and what is called a shadow block. So this dimension here, d minus delta, is called the shadow. So this is the shadow block. And so this, the nice thing about these functions is that they are single valued in Euclidean signature, while an individual block is not. So in d bigger than 1, a complete basis of single valued functions are these F delta L's. Let me write here that they are single valued in Euclidean, with L integer and delta being d half plus I nu, where this nu is positive or 0, so a non-negative real number. And so this is called the principal series. And now I can just decompose my correlator in this basis, in this complete basis, because I have a single valued in Euclidean function. So now I can write this as a sum over L and an integral. An integral in delta along this imaginary axis with some function times this box. Plus, so there's a little subtlety that comes here that this is true for the complete basis for normalizable functions. And G is not, the correlator is not, because of operator scalars of low dimension. So there's here some non-normalizable contribution that I need to separate out. So this is basically the identity and scalars with delta less than d half. Okay, and then the point of this complete basis is that it's orthonormal in the sense that if I integrate two of these guys together, then I get the delta function in the spin and a Dirac delta function in the imaginary part of the dimension. So, why we were doing this? So we had the correlator, which admits a block decomposition, but it can also be expanded in a complete set of functions for Euclidean single valued functions. So I expand the correlator differently instead of the usual block decomposition we were writing, but instead of this complete basis plus this non-normalizable stuff, now I can go between one and the other. And to go between one and the other, we see that C delta L, this function that I put here, it should be something that has poles where the physical operators are. like this. So it has poles where the operators are, and the residues are proportional to the OP coefficients, such that if I have, so in this representation, I'm integrating in the complex delta plane. When delta is a bit too small like this, when delta is equal to the half plus I, some imaginary number, so I'm integrating along this, let me draw it in blue, vertical line, where this is the half. And now I'm saying that this function C delta L has poles here along the real axis where my physical operators are. So I can now can recover the normal block expansion, normal conformal block expansion, just by deforming this contour such that I pick up all of these poles. And so I go from this presentation here where C delta L has poles with all the OP coefficients, poles where all of the operators are with residues that are minus the OP coefficient, such that when I close the contour like this, I just get the usual sum over blocks with.
Madalena, sorry, you have a question. Tushar, can you?
Yeah, so can you just define what delta K is? I missed the point. What are we are summing over delta K and L. So can you just explain what this delta K stands for?
Yes, sorry. So let me be a bit more clear here. So what I mean here is that, let me start again. So this C delta L has poles when delta is equal to the dimensions of your operators in the series. So if your series has operators with dimensions delta K and LK, these are the operators appearing in OP. These has poles in delta at fixed L when delta is equal to delta K. So I can write it near the poles. So then C delta L behaves near the poles as a pole in delta, as I vary delta when I reach the dimension of my operators, these operators. And then the residue is proportional to the OP coefficient. And now I was just summing over the set of operators in the series. Actually, this is a pair. Does this answer your question?
Yes, thanks.
Okay, then you have two more questions. Akil, and please go ahead.
Hi. Sorry, could you remind me what is a single valued function? What do you mean single valued?
It means that when I take Z and Z bar to be complex conjugates and I move Z around in the complex plane, then it's single valued, right? You go around and there's no branch cuts. I'm emphasizing this simply because if you remember earlier, when we were taking C and Z bar to be completely independent, we were seeing branch cuts and these things were not single valued. But if I take Z bar to be equal Z star, then the correlation function is single valued. So you can go around the Z plane and you always go back.
And the contour in the contour integration was a finite segment. Was it from d by 2 to d by 2 plus I?
This contour integral here?
Yeah.
So yes, here I'm integrating. So here yes.
It seems we need to deform it towards the real line, right?
I was deforming, yes. So I'm integrating. This is the complex delta plane. So now it's delta, not Z, and I'm integrating. So I sort of skip a step here, which is I can now write this as an integral from the half minus, I need, oh, okay, sorry, I realized what I did here. I wanted to integrate over nu from nu to 0 to infinity. So that's the vertical line I drew.
Okay, thanks. And a related question: what is this non-normalizable piece again? Like, what do you mean non-normalizable?
Good. So
This is subtracting the contributions from the shadow blocks, is it?
no, so the shadow block is what I'm about to correct now. I skipped one step in writing this. So these non-normalizable contributions are just stuff like the identity and low-dimensional scalars that, because these give non-normalizable contributions to the correlator, so they need to be subtracted because this is a complete basis only for normalizable functions, and G is not that. So what I skipped about the shadow is here that I want now to expand the range. Let me write it now like this. Where I now have, instead of the block plus shadow, just a block. So I just expanded it out and joined the two, because blocks and shadows are related along the principal series. They're just related by this being positive or negative. So this is one step, and then the non-normalizable still comes along. And then here, I have the integral I drew here. It goes from minus I infinity to plus I infinity. And then this is the contour that I will close to the right. And when I close to the right, I'm dropping the arcs at large delta, but the blocks go fast enough to 0 at these blocks. They die off as delta goes to large delta in the right half of the plane. Does this answer your question?
Yeah, thank you.
Okay, then maybe, hopefully quickly, Gabriel.
Yes. Hi, Madalena. So the C delta L, if I understand well, you can essentially find them explicitly through integrating the full correlator against the orthogonal blocks. So in that sense, are they? Is that the same construction as the Bell-Van Rees alpha space?
Yeah. So alpha space is again the same type of. Yeah, it's the same idea of trying to encode it, but it was a different space. But yes, it's the same idea of expanding this in some basis. And what you were saying about the C delta L's is what I will do in a minute.
Okay.
So I'm still relating all these ingredients. And I see there's one more question.
Yeah.
Sorry, Gabriel, did you have more?
No, thank you.
Joe?
Okay. Hi. My question is regarding the measure for the orthogonality condition. Can you write it down and give us some clue of how to compute it in general for?
Yeah, so the measure is written down very explicitly in the paper I quoted. I don't think it's very illuminating to write it down in the lecture, but you can, if you open that paper, you'll find it. So yes, here I omitted the fact that I'm integrating in Z bar with some measure, some appropriate measure, such that the functions are orthogonal. I was just highlighting the fact that what orthogonality meant.
Yeah, but in the paper is not really clear of how he computes the measure such that he has this orthogonality.
Well, it's okay. Maybe we can keep a discussion. That's a more detailed discussion that maybe I don't want to. But in essence, it's you're looking at eigenfunctions of a self-adjoint operator, which is the conformal Casimir, and this is how this is the basis.
Okay, thanks.
So the point is then, as I was alluded to, that these functions are orthogonal, so now I can just integrate this correlator against the pair. So there's a pair between this function and its orthogonal. And I extract this C delta else. So then C delta else are obtained with some, again, I'm omitting some functions. There are some normalizations that I won't write down, but I integrate over, I'm in Euclidean, remember? So it's equals Z bar star. So I'm integrating over complex Z over the complex Z plane with some measure times this. So this is an inversion formula, an Euclidean inversion formula. And if you want to then go into the details of the measure, maybe if you're not satisfied with this paper, maybe this one gives you a little bit more details on exactly this pairing. And you can also ask on Slack, but for the purpose of this lecture, I think I would like to focus on the big picture and not on the details of how to compute the measure. So I'm happy to discuss that later. But for now, you believe me that there is a measure. This is actually something old. It's been known for a long time. And it goes back to harmonic analysis and so on, that these Fs form a complete basis for Euclidean single-valued functions, and I can decompose the correlator like this. This is related to the normal OP decomposition by this closing of the contour argument and by having that C delta L has poles where the operators are. And then you can extract C delta L. So now I inverted OP. If you give me the correlation function, I now extract out this function C delta L. So this is what an inversion formula is. This is an Euclidean inversion formula. And this function is very nice because it encodes the spectrum. I just search for its poles, and its poles tell me what is the spectrum. And it encodes also the OP coefficients as the residues. Okay, so this was all Euclidean, and this is still something that was known for many years. So this is nice, but you need to tell me the whole correlator. If you tell me the correlator, then I can invert and I get this function C delta L. I don't know how to make progress if I only know particular information about the correlator. And moreover, it only is valid for integer L here. You saw that L was integers throughout in every equation I wrote. So this is valid for L is integer. And I need to know. So this still doesn't help me like I wanted. It still doesn't tell me what I wanted to learn. And this is where Karen Wall came in and got to this Lorentzian inversion formula.
You have another, hopefully it's quick, Hank, question.
Yeah, sorry, I don't understand, like in the conformal block G, you said that there are non-renormalizable contributions, right? And that part is good, but when you're pairing against F, those terms should also appear, right? So when you're computing C using the inversion formula, wouldn't that?
Yeah, yes. So yeah. I will always, you're right. I need to subtract off.
Okay, you're doing like a regularization.
Yeah, I'm subtracting off from G the non-normalizable contributions, and this is what I will be focusing on. You will see that the reason I was sloppy is that because when you get to the end, to the Lorentzian inversion formula, you really don't need to remember to normalize them, but that will become clear in a minute. For now, you're completely correct. What I'm expanding is G with some subtractions.
Okay, thank you.
So yes, minus. Okay, So this was an Euclidean inversion formula. Let's now go to a Lorentzian one. And the idea here is that, this looks wrong. Yes. No, sorry. This is embarrassing. Yes, now it's okay. Okay, so the idea of current voice, and then it starts from this Euclidean inversion formula. And he massages it, he manipulates the inversion formula until he gets a different expression that is now integrating not over Euclidean, but over Lorentzian configuration. So when the cross ratios are in Lorentzian signature. So then he gets the same function. This is still the thing we're after. This is what encodes all of our operators. And now it will be split into two contributions. And I'll call them CT and CU. Well, Simon called them CT and CU because they come from the T and U channel, but that's. And they are, where these functions now are computed again with some normalizations that I will omit, but now integrating over Lorentzian. So Z and Z bar are real and independent with the measure. And now the kernel became modified. This is a block, the normal conformal blocks we've been writing, but notice that usually this is the dimension and this is the spin. So this dimension and spin got swapped on top of these shifts by the space-time dimension. Times, and now the double discontinuity. And I will introduce what all these ingredients are in a minute. So I'm just writing down the formula. And now I'll introduce what all of these things mean. So the nice thing is that now we're extracting this thing, this density, this OP density, if you will, from a formula that is manifestly analytic in spin. So now these CT delta L's are functions that are analytic in spin. The spin went in that entry there. So this is but notice that it's for the even and odd family, for even and odd spin separately, because the whole formula that I wrote here has this -1 to the L. So, there's one comment that I need to make is that this formula is only valid, is only guaranteed to be valid for spin bigger than 1. Essentially because in this derivation, some arcs were dropped, and those arcs, these arcs in the contour of integration can only be dropped if L is bigger than 1. Now I'm just stating the result that Simon derived, and I will give a flavor of how it's derived in a minute. But before that, let me just draw the conclusions and also introduce all the ingredients that appeared here. So. And then the thing I need to introduce is that this D disk appeared. So what is this D disk of G? So let's think about the complex D bar plane. So and I will draw both Z and Z bar in the same plane. I'm mostly interested in Z bar right now. So I was in an Euclidean configuration, so Z and Z bar are complex conjugates, but in some point in this derivation, we went to Lorentzian, so we made them independent, so we had to continue in Z and Z bar. And what happened is that we ended up with this double discontinuity, which is if you take Z fixed and you look at the Z bar plane, you can evaluate the correlator. So this is one, this is the cut we saw earlier. And I can evaluate the correlator there. So this is just evaluating the correlator at some value between 0 and 1, which is where I'm computing the function. But I can also get to that point on the second sheet. So I can take G and continue to the second sheet and evaluate there. So this is basically take Z bar, go around the cut, and then come back and evaluate it on the same point. Or I can continue in a different way by going the other way around. So this is now going the other way around the cut. So I'm comparing the different continuations of Z around this branch cut that starts at 1. So this is what a double discontinuity is. You can also think of it as some double commutator of the operators in Lorentzian signature. And this is the thing that appeared after all of these manipulations. Okay. So then this established that the CFT data organizes itself in this function that is analytic in spin. So it's encoded in this function that's analytic in spin. And it's computable through some kernel against the integrate. So by integrating against some kernel, the double discontinuity of the correlator. And this double discontinuity, which in practice is evaluated like this, is something that is actually positive. So it has nice properties, and it has a bunch of other nice properties that I will discuss in a minute. But now I would like to connect to the story we've been hearing, to connect to the light cone. So where is the light cone? I promised that somehow we would get the same answers here. So where is the light cone? Basically, how does this formula help? So now if you take L much bigger than 1 in C delta L, you just go to the expression I wrote down and you take large L here and you see what happens to these integrals, and you will see that the kernel will actually project the integral for a region where Z bar is near 1. But Z bar is near 1, if you remember, of the correlator is exactly the light cone. So when L is very large, the kernel projects the Z bar integral to Z bar near 1. So G of Z bar needs to be evaluated near Z bar equals 1, which is the light cone. So now I no longer need the whole correlator if I just want to know something about large spin behavior of the CFT data. I just need to know, I recover what we saw intuitively with the light cone, that if the large spin behavior in one channel is related to the low twist in T channel, which is what dominates this light cone when Z bar goes to 1. So this means that when you're evaluating the disk of G, now I want to, the idea here is to try to get information out of the CFT without knowing the full correlator. Of course, if I know the full correlator, I can just expand in blocks and I know everything there is to know. But in practice, in real life, I don't know the whole correlator, so I need to make do with some limited information. So I get here, and I could just try to do an expansion in S-channel blocks, but then I would find that the double discontinuity of each individual S-channel is 0, which is related to the fact that these operations do not commute. And what I should do instead is represent the correlator by its T-channel. So here you do, you write PFZZ bar in a T-channel expansion, just like we were doing in the Litecoin bootstrap. And now when you send Z bar to 1, you again discover the leading twist, the lowest twist operators dominate, and you recover everything from the Litecoin bootstrap. You recover the Litecoin bootstrap. And if you want to work in a perturbative expansion in 1 over L, then you expand this in powers of 1 minus Z bar, and you go on, and it's just the same as the Litecoin bootstrap. And this in particular gives you an asymptotic series in 1 over L. But we can do better now because we actually have the whole inversion formula. So there's no need to take Z bar to 1 and L large. We can just extract the contributions to C delta L of given T-channel operators at finite C. So not taking the Z bar to 1 limit. So now what we are writing, now we can do better. We don't need an asymptotic expansion anymore. We can just do the following. So I was inverting the S-channel OP. So I get the S-channel OP data in terms of some integration of the double discontinuity of the correlator that I now compute using the T-channel. And I can now comment back to the point about the subtractions. Because the double discontinuity of S-channel block is 0, which I'm claiming, I haven't shown, but it's true, then I can forget that I had to do subtraction. So I don't even need to know what I had to subtract. Those things will just drop out. Okay. We are now in a similar position as the Litecoin bootstrap. If we take large spin, we will see again that the identity operator will predict something. But now we can do better statements because we're actually talking about a function that has poles where the operators are. So we're now talking about the full CFT data. We can make now statements about individual operators. So we now discover that the operators organize themselves in trajectories that are analytic in spin. So these are called Reggie trajectories. And what we were seeing in the Litecoin is that the trajectories that dominated as L was very large. So we were finding the end of those trajectories, the asymptotic end of these trajectories at very large L. But now all operators should lie in these trajectories. So I can now draw some plots like this. This is the spin. Let me draw here d minus d half. And now all operators must lie on some trajectories. And again, because of this dropping of the arc story, this is only valid for L bigger than 1. So that's why I stopped drawing the curves, but then all operators lie on trajectories and at integer even spins, because I was considering identical operators. We have our operators, but there's some rigidity now. Now we see how they align in these trajectories. Okay, I drew this side here because of shadow symmetry, but I won't have time to go too much into that. So these are Reggie trajectories. Yeah. Is there a question?
10-minute warning. That's all.
Thanks. Yes, so I'm going to start wrapping up now. Okay, so now this inversion formula tells us how the CFT data, which is nicely encoded in this function, has to organize into these trajectories for spins bigger than 1. And these essentially came from when we derived this formula. We had to drop some arcs, and these arcs can only be dropped if the spin is large enough such that they go to 0. So when the spin goes below this, what we're missing in this formula is incomplete. You need to add the arcs. And the arcs can either give a finite contribution or an infinite contribution. So we're really not sure what happens below this. This is the generic behavior of a correlator. You could have correlators that behave nicer, that are faster in going to 0 in these arcs that you drop. So it could be that this behavior is actually better in particular models, but this is what's guaranteed just by conformal symmetry. And now the thing you probably want to ask is how much of the function do you need to know? If you want to know about large spin, you just need to know about low twists, but then you want to have some procedure to reconstruct the CFT data from a little knowledge of the spectrum. And this is where this formula is nice, if you're working in perturbation theory. So the double discontinuity has some nice properties. And I will just outline a few of those properties. So if you have double discontinuity of T-channel double twists, so remember that double twists are operators that have dimensions equal to twice the external one plus L plus some integer, then the d-disk is 0. So what does this mean? This means that if I'm studying some theory perturbatively around a point where the theory is essentially free or generalized free, in which all operators are exact double twists because it's a free theory, then in the exactly free or generalized free point, the only operator with a non-zero d-disk, and maybe let me write it as I was doing before, is the identity. And this gives, as you can predict, the double twists, just like the light cone bootstrap. And the double twists are there, but they don't contribute. So I should have written here plus the double twists, but in the end they drop out because of double discontinuity, and I just need to know the identity and I recover everything. And now I want to do some perturbation theory around this point. So now I imagine that all operators will get some small anomalous dimension controlled by whatever perturbative parameter I have. And this means that I will now have to do the d-disk of the identity plus this double twist with the small anomalous dimensions. And double twists we were seeing contribute basically as 1 minus z bar. So if you now recall everything we said in the light cone, things were contributing like this. But now if they're approximate of double twist dimension, I get 1 minus z bar to the double twists. And then again a log of 1 minus z bar. But logs turn out to also have 0 double discontinuity. So they don't contribute. So at leading order, let me write now in first order in some perturbation. What do I get here? I get that it's a d-disk of the identity plus the d-disk of logs, which is 0, and plus some new operators that might appear. first order. And this is all you need to know to recover the spectrum, the S channel, to read off the S channel for L bigger than 1. Okay, a little caveat here is that L bigger than 1 is what is guaranteed for a full-fledged conformal field theory. If you're working in perturbation theory, you should worry if each order in the expansion of your correlator actually weakens this bound, and this can and does happen. Okay, so these were a few nice features of double discontinuity. And the practical nice use of this inversion formula. But in the last 5 minutes, maybe let me summarize and also touch upon some of the new developments. So what did we get? So I told you, and I didn't really outline much of how the proof goes, but I told you that there's a way to extract the CFT data from some integral of a double discontinuity of your correlator. And these established, this manifest analytic in spin, so this established the existence of Reggie trajectories. But now this is analytic in spin, and I'm telling you that when L is even or integer, this is where my operators are. But is there a meaning for this function? So this CFT, this function that captures the CFT data can be continued in spin. Is there a meaning to the continuation for non-integer spin, or does it only have a meaning for integer spin? So when I was drawing these plots of L versus the dimension, I was drawing dots where the operators are, but is this meaningful? Are the lines in between meaningful? Can I continue the operator in the same way I can continue the CFT data? And the answer is yes. So or L not integer. And these are called light ray operators. And this was established in this reference here. Then another thing that you can ask is, okay, I'm recovering the CFT data from just this operation, this double discontinuity on my correlator. Can I now go back and just recover the whole correlator from its double discontinuity? The answer again turns out to be yes, otherwise I wouldn't be asking it, and this goes under the name of dispersion relations. So this is writing, recovering the correlator as some integral, again, with some kernel of the double discontinuity of G. So this was done here. And there are more references, and then the first talk on Monday, I believe, will touch upon precisely this. So then you can recover the whole correlator from its double discontinuity. Again, here there are some subtleties related to the fact that the spin the spin 1 bound we had. So you might have to, there might need to be some appropriate modifications of what you're relating, and it's not exactly the correlator. And to be completely precise, I should write instead here ZZ bar. Oh, I'm sorry. Of course, this is nonsensical. I should have written W, which is what I was integrating over. Okay. So this has been something that has been, these dispersion relations have been recently studied quite a lot. So this will be the subject, I think, or part of the subject of Rastelli's talk on Monday. And then, as always, you can do more things. You can add supersymmetry, and supersymmetry makes life easier. It makes these inversion formulas sometimes work for all spins, not just spin bigger than 1. But yeah, I think this is where I want to stop and take questions.
Okay, great. So let's big round of applause for Madalena. It's the last lecture, so click on your reactions. Very good. Excellent. Thank you so much. This was great. Yay. And even we got a little, okay, in any case, thank you for the applause. Thank you, Madalena. So now let's start with the questions. And we have one from Gabriel.
Hi again, Madalena. The story of the spin of the L greater than 1, is that the same thing as the discrete series that has to be added to the G?
No, the story of the L greater than 1 is it's really these arcs that were dropped, so it has to do instead with the Ricci limit of the correlation function.
Okay, so because obviously in one dimension the whole story is a bit different. I know that one of the main challenges that we have is this whole story of the discrete series that you have to add on top, because obviously at first order in perturbation, for example, the double discontinuity of the G is 0, but the actual function G is not vanishing at that order.
Yeah, 1D is substantially different. That's why when I was writing these completeness relations, I think I actually wrote D greater than 1.
Yeah,
so then you're right that there's this extra discrete series that you need to add on. L bigger than 1 here is a different, it comes from a different region, from a different cause. Yeah.
Okay. Thank you.
And if people have questions, I know this part was more of a flavor of what the inversion formula is, but if you have practical questions, there's still the Slack channel. So thanks for everyone who's been asking questions there. It has been very nice to have such a discussion, and we can keep having that discussion there.
Let's see.
Is there time for question? I have a question.
There's someone with their hand raised right now. So let me, we'll do Tusha and then Dimitri, if that's okay.
Right, so just to understand the picture here. So in the previous lecture, we saw that how using this light cone bootstrap method allows us to get the spectrum of operators at large spin. However, here the point is that using this inversion formula allows us to get the spectrum of operators even for low spin L greater than 1. Is that the idea here?
That's definitely the idea. Of course, so what we were trying to see here is that, so in the light cone bootstrap, we were saying that large spin in the S channel is controlled by low twist in the T channel. And here is still the same. So if you only have limited information about your 4-point function, and in particular, if you only have the lowest twist operators in the T channel, you're only getting partial information about your S channel. You know that this information becomes better as you crank L up to infinity. but you're no longer working in an asymptotic series in 1 over L. You're just getting the contributions. But it's still, if you just know limited information about your correlator, you're still making an error because you're still losing some information about, there's still stuff that contributes, and these contributions become bigger at lower spin. Does this answer?
Okay.
Dimitri, you had a question?
Right. Yeah. Sorry. Thank you for very nice lectures, and sorry for being a bad student. I have a very basic question. So when we compare the expansions in the T and S channel, so this is what you've done in the end of the last lecture and the beginning of this lecture. And we make the conclusion about the existence of the double twist operators in the S channel. So what exactly do we compare? So we have two expansions and they look different. So which terms in this expansion do we compare?
You mean already not now in the language of the inversion formula, or still in the language of...
even before in the original Lightcon bootstrap.
Here. So here what we're comparing is computing this correlation function using two different OPs. This OP is the S channel, and this OP is the T channel.
Yes.
And I'm taking a particular limit that projects this channel onto the lowest twist operator, so that the dominant contribution in the T channel is the lowest twist.
Right, that's in T channel. And then we should see this identity operator in the S channel. So
yes, how does the T channel identity operator become reproduced in the S channel is what tells me about large spin.
So, and how is it? I imagine it is not just the identity operator. It's just should be an infinite sum in principle. What to do, resummation.
Yes, so this is one of the things that a finite number of S-channel blocks, as we said, cannot reproduce this contribution. The T-channel identity cannot be reproduced by a finite sum of S-channel operators. If you're asking about the S-channel identity, is still there, but this limit I took is making its contribution not important. Because in this limit, it's large spin that is dominating the sum.
Right. So what exactly how exactly I conclude that there is the identity results in this double twist operator manifest in this S channel?
This comes from matching first the powers of Z. So the identity is contributing as a Z to the delta O, whereas S channel operators contribute like this.
So it's the same expansion in Z after all. Yeah.
Yes, so this is the limit I'm taking, Z bar to 1 and then Z to 0.
Okay.
So it's the same expansion, yeah.
Okay, very good. Thank you. Yeah, I think I got it now.
Okay, very good. So thank you again, Madalena. We'll miss you, but we'll have you in Slack. So as she said, please ask her more questions through Slack. And yeah, thank you so much for these wonderful lectures and all the discussions and answering all of our questions. It was really a pleasure to have you here. And so last round of applause. Clap, 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 clap.
Thank you.